Welcome back to Wood Engineering. I'm Jeff Arochko from Carleton University, and in this video, we're going to finish up design of bolted connections by talking about splitting failure mode, which is the only one of those failure modes that is a perpendicular to grain specific failure mode. Then we're going to summarize everything after that. So what's splitting? So splitting is not so easy to come up with the simple mechanics of how to do this because it's based on a fracture mechanics approach. So the equation is a bit opaque for us from a mechanics point of view, unless we have background in fracture mechanics. So I'm going to describe what happens, and then I'm going to give the calculation procedure. So, okay, so here we have a piece of wood. Now we're looking at it on its side, and we have bolts inside this piece of wood. And now instead of the bolt wanting to tear out the side, for example, or have group tear out, or net tension, or even bolt yielding, we're looking at what happens if the bolt wants to move perpendicular to grain. So I'm pulling down, which means that basically I'm grabbing this wood and pulling it down, okay, from a certain height. I'm pulling it down. Okay, so we know from when we talked about connections in general that this is a very bad way to load a piece of wood if we can possibly avoid it, because if we have our straws, comme ça, then if we want to pull down, if we're pulling down, like if my fingers here are the bolts, and I pull down, or actually why don't I just put a bolt in there? Let's say I put a bolt in between these straws. Okay, great. And now I pull down on that bolt. It's basically going to open up this crack. Okay, so it's going to want to pull all of this stuff on the bottom down, which is going to open up the cracks on this side and this side. Bit messy with the straws. If I draw it, I think it'll make a bit more sense. So if we pull down those bolts, what's going to happen? We're basically going to form a crack here because we're splitting apart the fibers. Okay, so that crack is going to have some certain length. And then if we pull enough, it's basically going to split the piece of wood crossways, which is very bad. So when we do this, we need to look at our unloaded edge and our loaded edge, and we're going to use these distances to calculate our splitting strength. So first of all, let's recall that the depth of this piece of wood is D. Okay, and then I have two different distances here. And this depends on the way that the bolts are going. Okay, so here we have our EP. And recall that EP is our unloaded edge distance. Oops, unloaded edge distance. Okay, we have a loaded edge distance too. That's this one, but we're not going to happen to use that. That's our EQ, which we talked about before. Okay, so we're not going to use that here. What we're going to use is this DE, which is our effective depth. And this is the same dimension that we used when we talked about calculating shear strength at connections in one of the previous videos. So this is effective depth. And that equals D minus EP, minus our unloaded edge distance. So remember, it's the distance from the farthest bolt to the loaded edge. And just to remind us of that, we're going to recall that in this connection, since the bolts are pushing downwards, this is our loaded edge, and this one up here is our unloaded edge. Okay, so given those definitions, now we can calculate what the strength is. Okay, so just like when we talked about row shear and group tear out and net area, we talked about the fact that we only calculate for one side of the connection. And when we're talking about perpendicular to grain load, this makes even more sense because here I now have a connection. Let's say I have this member basically hanging from this member, and I have connected them with two bolts. So here I have two small convenient holes. So let's say the bolts are at similar locations to that. So this member now is hanging from this and it's pulling it down, and I have a bolted connection between them. So I have one side of the connection here, and I have the other side of the connection here. Now, obviously, in this case, calculating the strength on one side of the connection is going to be very different than calculating it on the other side, right? Because for this horizontal member, when this pulls down, the bolts are going to want to pull down, and I'm going to be splitting this member apart. And so for this side of the connection, I'm going to calculate the splitting failure mode. Now, what about for this member here? This member is connected with 2 bolts, for example, and when this member pulls down, the bolts are going to want to stay there, and the bolts are going to pull up in this member, right? They're going to want to pull up. Okay, so as this member pulls down, the bolts in that member, which are restrained by this one, are going to want to go up towards the end of this member. So for this member, I'm not calculating splitting at all. For this side of the connection, I'm going to calculate row shear. I'm going to calculate net tension, right? So for 2 sides of the connection, they could be 2 different materials, and they could also be in 2 different directions, which means that I'm going to use different calculation method to calculate the strength of each. Okay, so that's a little bit maybe less confusing than this case where I have both sides of the connection are loaded kind of in the same direction, but I still am considering this side of the connection for one calculation, and then I'm going to calculate this side of the connection separately. So same thing. But maybe it's a bit clearer when you talk about it in terms of perpendicular to grain. You know, if I have a member that's hanging that is in a different direction. Okay, so for one side of the connection, I am going to do this calculation. So usually, you know, I think it would be pretty weird to have 2 members connected together in perpendicular to grain, and they both have splitting loads. That would be pretty strange, probably. Okay. Okay, so for each member on that side of the connection, so if I had, you know, what's the case that I could have 2 members on that side? Okay, what if I had 2 members like this, and I had a plate in between, and the plate was then hanging? That's a case where I would have 2 members on one side, those would be the splitting ones, and 1 member on the other side of the connection, which is the one that's pulling down. Okay, so then I would have 2 of these to add up. Okay, so I'm going to calculate the splitting resistance, and the equation is like this. So QS, Q is for perpendicular to grain, S is for splitting, R resistance, I member I. Okay, we're going to have phi W for a brittle failure mode, QSI, and then KD, KSF, KT, which we are, of course, used to having all of those. And then phi W is 0.7, like we've seen before. And this is the fracture mechanics bit here, 14T dE divided by 1 minus dE over D. Okay, so you can see that there's no effect of the strength. It's only geometry. So that is not what we're used to. Okay, so I plug all those things in and I get my splitting resistance for that member. And then if I have multiple members on that side of connection, I'm going to repeat it for the other member on that side. And then I'm going to find the total. So Q for perpendicular, S for splitting, R for resistance, T for total is the sum of all the individual resistances for each of the members. And that's it. That's how I get my QSRT, which is my total perpendicular to grain splitting resistance. Okay, so now we have finally accomplished calculating resistances for yielding, for row shear, which is parallel to grain, for group tear, which is parallel to grain, for net tension, which is parallel to grain, and the last one for splitting, which is perpendicular to grain. So if my loads are all parallel to grain or all perpendicular to grain, then it's pretty straightforward. You know, I just have to make sure that my parallel to grain resistances are greater than my parallel to grain load, and also that my yielding resistance is greater than my parallel to grain load. But what if my load is on an angle? So I have one component that's causing parallel to grain stresses and one component that's causing perpendicular to grain stresses. Well, then we're going to have an interaction equation for that. That's going to be part of this summary that I'm going to do next. And the summary is nice because you can basically follow along and say, I satisfy this, I satisfy that, I satisfy that, I satisfy that. And as long as I satisfy all 4 requirements in that summary, then my connection is good to go. Okay, in the code, in the standard, sorry, it starts with this at the beginning of 12.4, which is the bolted connection section. I like to end with it because it kind of summarizes everything. Okay, so here we're going to revisit all of the different resistances that we've already calculated. Okay, so the first one is for yielding. And remember, for yielding, angle to grain is taken into account in the calculation of NR, the yielding resistance, because the embedment strength for wood takes into account the angle to grain. So it's all built in. So all I need to know here is what's the total load at whatever angle it exists at, and then what's the total resistance, which is at the same angle, because I take that angle into account when I calculate NR, which is my resistance. So the NF here is in any direction. Okay, so then I look at all the parallel to grain components. Okay, and then I have my PF. So let's look at what this is. Okay, so here is my, if I have a piece of wood, say some random place within a piece of wood, and I have a bolt here. Okay, and let's say that my load is on an angle. This is NF. Okay, that's my total load. And I have an angle here of theta, which is between the grain and the load. Okay, then I can split that NF into two components, right? One being the PF, which is the parallel to grain component, and one being the QF, which is my perpendicular to grain component. Okay, let me neaten that up a little bit. Okay, so these are the NF, the PF, and the QF that we're talking about when we're doing these checks. So for yielding, I use the full NF, right? For parallel to grain, I'm going to use only the parallel to grain component of that load NF, and I'm going to check it against all my parallel to grain resistances. Now in the standard, instead of PR min, it just says PR, but I like to write it as PR min because PR min is a minimum of all of the different potential parallel to grain failure modes. So we have PRRT, we have PG, let me make these a bit bigger. We have PG, which is our group tear out, RT, and we have RTN, RT, which is our net tension. Now we might not have all three of these for every case, right? Because, I mean, row shear will basically always have, as long as we have more than two bolts in a row, or more than one bolt in a row. Group tear out we'll only have if we have a tension load where we have a loaded end, right? And same for net tension. We'll only have that if we have a tension load with a loaded end, right? Because we can't have net tension in compression, obviously. Okay, so I calculate all of those that apply, and then whichever one is the lowest, that's my PR min. So that's my lowest parallel to grain resistance. PR min, I'm gonna just write in here that this equals PR for this code because we're gonna use PR later. And I compare that against my PF, which is my parallel to grain component of the total load. If all of my load is parallel to grain, then NF equals PF, right? And my QF would be 0. And I will provide also the clauses for these. So we have them all in one place. Okay, so that's the parallel to grain. Then we do the same for perpendicular to grain. Okay, so in this case, there's only one perpendicular to grain failure mode, which is the splitting failure mode. So QR is just equal to QST, which happens to be the one for splitting. Okay, now, so those are all our failure modes, right? We had yielding, we had row shear, group tear out, net tension, and splitting. Okay, now the very last check that we need to do is one that we need if we have both parallel and perpendicular components. Okay, so there's no need to check this one if I have all of my load being parallel to grain or all of my load is perpendicular to grain, right? Because then NF equals QF or NF equals PF. But if I have it at an angle to grain, then I need to check this interaction. Okay, so then I'm going to use my NF, which is the total load, right? It's the load that's on the angle, NF. Okay, and I'm going to compare that to this interaction. Okay, and you'll recognize this interaction as being the same interaction that we use for embedment strength. Okay, PR QR divided by PR sine squared theta plus QR cosquared theta. And you'll see that if I set theta equal to 0, then I'm going to end up with NF less than or equal to PR. And if I set theta equal to 90 degrees, then I'm going to say I'm going to have NF less than or equal to QR. So then all I have to do is I check A through D, whichever ones are applicable. Usually, A, if I'm just parallel to grain, then really I only have to check A and B, right? If I'm just perpendicular to grain, I really only have to check A and C. If I have an angle to grain, I have to check all of them, of course. Then once I check all of those requirements match, that my resistances are all greater than my factored loads, then my connection is done. So that brings us to the end of bolted connection design. We've looked at our spacing requirements and geometry. We've looked at the mechanics of each of these different failure modes: yielding, failure mode, which does not depend on parallel or perpendicular. It doesn't matter what the angle, and it applies to the entire connection. And then the rest only apply to each side of the connection, as we talked about. We have the parallel to grain failure modes, which are row shear, group tear out, and net tension. Then we had the perpendicular to grain failure, which was splitting. And then just now we looked at what happens if we have load that will cause potentially parallel to grain failure and perpendicular to grain failure, in which case we check this final interaction equation. And then once we do that, we're done. So next we're going to look at some examples of bolted connection checks and designs to get our feet wet on these equations.